According to our friend Wikipedia, a synergy is the interaction or cooperation of two or more organizations, substances, or other agents to produce a combined effect greater than the sum of their separate effects. It is the creation of a whole that is greater than the simple sum of its parts. Complex engineered systems are composed of many diverse components, and when we say diverse, we may be talking about components that were never designed to interoperate. Think of the Internet. It is called the network of networks. Many of those original local area networks that were built for hospitals, businesses, or factories were designed with their own internal logic. When they were built, no one thought about how one day we might be connecting them all together. Thus today, we have the huge challenge of opening all these information systems up and exposing their data and functionality through common interfaces. Designing these heterogeneous composite systems is a bit like being a DJ taking a song by the Beatles and mixing it with Nirvana and Fatboy Slim. We have to somehow make them work together seamlessly for the end user, somehow overcome all this diversity, difference, and general messiness, and we do this by designing the relations between the components. Relations can be fundamentally of two different types: synergistic, that is, constructive or destructive, what we might call relations of interference. So let's take an example of both. Destructive relations represent the interference of two or more components within the system. An example of this might be a crossroad intersection. For traffic on each road, the other road is essentially an interference, slowing it down and stopping it on its way. This is what we call a zero-sum game. When the traffic on one road gets what it wants, then the traffic on the other loses, and vice versa. There are many examples of zero-sum games in the systems we engineer. From noise pollution to overpopulated cities, we are always trying to avoid the development of these zero-sum games and the relations of interference that lead to them. In contrary, constructive relations are synergistic. That is, when two or more components interact and the net result is beneficiary to both parties, resulting in what we might call a positive sum game. Each gets out of the interaction more than they put in. Examples of this are social networks. The more that join, the more valuable the network is for any individual user. Many forms of economic trade are also positive sum. What we're trying to do then in designing these networks is to make positive sum games the attractor state. That is, the state towards which elements within the systems will naturally gravitate. Of course, this is easier said than done. It requires a significant investment in the system's infrastructure, that is, the relations through which the elements interact. To illustrate this, let's think back to our example of the road crossing. How could we avoid a zero-sum game here? Well, engineers have already figured this one out by creating a flyover with ramps connecting the two roads. We now have a positive sum game, but it took intelligent design and significant investment of resources. This was not the default position. Alternative technologies might be another example. Whereas many of our traditional technologies create a zero-sum game between human needs and ecological needs, well-designed alternative technologies try to change this by harnessing synergistic relations. Another factor these examples might illustrate is the importance of nonlinear or parallel systems in creating synergistic relations. In simple linear systems, everything requires the same input and produces the same output. The result is a linear process of inputting resources from the environment and outputting waste back to the environment. Of course, we are all familiar with this model as it represents the fundamentals of industrial economies. In order to create synergies, there needs to be some diversity in the system, that is, processes taking place on different, parallel levels. In this way, different components in the system process different resources, and it may be possible to connect what is waste for one component to what is an input resource for another, thus turning what is often a zero-sum game of competition over one resource into a positive-sum game where the more one consumes, the more the other can also. Of course, ecosystems are the classical examples of this, and being able to model and develop these synergistic cycles, both on the micro level and on the macro level, within our industrial systems is key to achieving sustainability. In the design of these complex systems, the huge heterogeneity and diversity of components is a key challenge. We may be dealing with widely disparate and qualitatively different socio-technical components. Instead of working against this by trying to dumb down the variation